Good evening, everyone. My name is Gurgen Hovakimyan, and I'm Staff Research and Development Engineer in Synopsys, and also I'm a PhD student in New University of Lisbon. And when I was preparing today's Meetup talk, several of my friends were asking what is it going to about, to talk what is it about. And to understand it better, maybe probably from the title it will be a little bit difficult, or if I will just give the interpretation of the concept drift, it will be, not so easy to understand. So that's why I prepared 3 blitz questions for you. First one is, let's imagine that we are working on some classification model, and we have such simple data set, and if I will ask you, can we easily separate this data? You will say probably, yeah. We can use some, for example, tree-based model, and with very high accuracy, probably with some points that will be here will be misclassified, but in general, it will be easy to create a classification model for such problem, for such data. Now, let's make it a little bit difficult. Let's say we have not classes as group 1 or group 2, but let's imagine that in these groups, we have classes like this, 0 and 1, and our problem is to make classification on this data to separate the class 1 and class 0. And you will say, okay, in this case, I can use groups as an indicator, and then also in this case, it will be not a big problem to make a classification, so with some tree-based models, and it will be not a big problem. So now let's look at this from another perspective. So let's imagine that when you are training model, your initial data set contains only points from group 1. And then you need to put this in production, and you will receive some data from group 2, group 3, and etc. So unique groups every time. Now, let's say you are creating some classification model, pretty straightforward to classify this, just to separate class 1 from class 0. And in this case, it's very easy to separate, but let's remember that in our previous slide, we had the case that our data shifted, and now we created the classification model on this part of group 1 data, and then when group 2 data arrives, and you just put it in the production and it stays like there, now your model starts to work not as expected. So what happened in this case? Our data, initial data, that looked like this and had range from -3 to 3, changed the distribution, and now the range is, a little bit different. And now in this case, it goes up to 6 for the feature 1 and for feature 2 the same. So what happened? Happened the fact that in our case, we created a model that was trained on some data and was easy to separate, and then our data distribution shifted, and this caused the problem known as concept drift. So when we're going to talk about around 40 minutes about the concept drift, about this problem when you are training a model and then after some time you receive new points in your production database, and you'll see that your classification model starts to degrade because your distribution changed, and this caused problem of accuracy of your model. So there are 2 main parts that we're going to discuss today, and first part, it will be about the main idea of the concept drift, and this has 4 subsections, and the second part is about the case studies. We'll look into examples to understand how it works, how we can detect the drift and make models to work better. So first thing that I want to do, that first time that I saw this problem in one of my researches, I found out that it was, something new for me, and at that time I was thinking, okay, how am I going to do some literature review? And normally what we do, we just Google some topic, the name of the topic, and we look into the papers that we receive. But in this case, I want to spend around 2-3 minutes to explain something else that related to systematic literature review that we did for this specific topic. And I believe this will be useful for everyone because you can use this main approach not only for this case, but also for any topic that you are interested in. So, about the systematic literature review, what we understand with that? There are several different ways that how people do the systematic literature review, but for me personally, one of the best approaches is Prisma. That includes several steps that I will describe now. So, generally speaking, you can describe it with this type of graph, where initially you have to identify the main topic, the papers that you want to review, then just look into them, understand probably from abstract keywords if they fit in the topic that you are interested in, filter out some of them that are not relevant, or maybe there is some language that you don't understand. For example, you speak only in English and there is something in Spanish, let's say. And then you maybe will check out how many citations it has and etc. And then based on it, you will decide, okay, I'm going to read these papers and find out which are the state of the art of the models of the specific topic that you are interested in. So this is mainly how it's done. But in this case, we decided not to go just like straightforward with just Googling and finding out the papers, but instead of that, we decided to use IEEE and Science Direct APIs that allows us just to provide some keywords. For example, in this case, concept drift, drift detection, etc. And then, based on your provided keywords, you will receive large volume of data where there are described some papers that were published and printed in IEEE and Science Direct. So in this way, we extracted around 450 papers instantly, where all the topics were related to a specific our case. So additionally, beside this, we also use some other sources, and for this, unfortunately, we were forced to use just simple search options to extract some data. And then after that, how you are going to understand, okay, we have 450 papers, how we are going to just remove, review all of them. It will take very long time. So what we do first, we first should understand which are the most relevant or most cited, and for that case, you just can review not only the abstract, but also take into account how many citations it has and when it was published. Because one thing is the paper that was published 1 year ago and it has 10 citations, and completely another thing that the paper that has 10 citations and was published 10 years ago. So you can just calculate the ratio and sort it by that threshold, and then understand, okay, I'm going to use the papers that are published only after 2004 and have at least 20 citations, for example. So after these steps, there can be also additional steps that you might find some specific for your specific case. That, for example, lack of data, that, okay, they're describing some findings, but there is no data that you can replicate the results, so you can just eliminate some of the things. And in the end, you can just have some sample of papers that you can review. So this is the main approach that I wanted to mention how we're working on this specific case. And there were 65 papers that we decided to include in our research. And this is the main approach how we are doing it. Okay, after reviewing all the papers, we find out that there are two main approaches that scientists decide to separate concept drift. So first one is based on the distribution. So now I believe it will be easier to understand the main problem from the graphs. So let's say we have initially this data, original data distribution, and we're creating some classification model to separate the stars from these blue dots, blobs, and pretty straightforward. So what can happen after some time? We can have some type of drift called virtual drift, where our classification model continues working fine. However, our data, our features shifted. So initial distribution was like this, and then it became like this, and for the stars, it changed like this. This is one of the cases that's, a lot of scientists will say that, it's not a big problem until my classification problem works fine, my classification model works fine, so not a big deal. Another thing that can happen, this one is very specific, I will talk about this one a little bit later too, when you are creating some model for two classes, and then after some time there is a new class that you have in your data, and if you don't update your model, what will happen? That you will classify it, like for example in this case, as a stars. And the most severe type of problem that appears is real drift, where our model completely degrades and accuracy significantly drops. So in this case, our model, if we don't update it, our classification, decision boundary will be this, and if our data becomes like this, it will be a significant problem for us. So another option how you can just to separate your data is based on the time, because it's also important to understand how fast is changing your data. Because if you will understand how fast it changes, you will understand how often you have to update your model. So that's why there is also called time-based separation. So easiest straightforward thing that, easy to notice is sudden drift, where your data distribution instantly changes, and in this case you will notice the data distribution change very fast. Another thing that happens too often in real data cases, incremental drift, where our data distribution changes slowly, that initially you don't notice anything wrong, and then after some time you see that your classification model is completely wrong. Also, recurring drift. This one is, probably one of the most popular ones, and everyone probably can guess what is it about. So most of the cases that happen like this is some seasonal patterns that we have in our data case. So for example, in summer, your data behaves in another way, in winter in another. For example, in case of tourism. And gradual drift, that initially you may have data like this, and then just once some peak, then it becomes as in the past, and then it changes completely again to the new version. So there are actually different examples that we can bring from finance, healthcare, recommendation systems. So for example, in finance, if you are working in, with the data sets that have, you're trying to detect if the person will cover his mortgage loan or not. And if you created your model in 2010 and now you are using it, probably it will not work as fine as now if you will update it and use more new data. But my favorite example is related to recommendation systems. Let's imagine that we have someone is using a dating application, and he's interested on a person that is interested also in history, Lego, and etc. And he finds someone, and after some part of dating, he understands that it's something that he wants to find new person with new interests, but the dating application continues to recommend him the previous person with the previous interests. So in this case, that person maybe will not find the correct person that he wants. About the image classification, we'll talk a little bit later, because there is a larger example that I prepared. So, during the Q&A session, if you name a topic field, I will name a case where it can happen, some type of drift. Okay, about drift detection methods. So probably everyone knows R&D from AI deep learning networks, and this person, Joe Gama, is probably the most, on my personal view, is the most famous scientist in the field of concept drift detection. Because when we're making literature review, we noticed that his papers are the most cited, and there were a large volume of papers that he published, and actually I'll speak about him a little bit later, but he is a scientist and works in University of Porto, and that's why I decided to show him. Because if you will be interested and you will think, okay, which papers I should review, definitely you need to start with his papers. So there are different methods how people handle concept drift. So main idea is that you can classify them based on some type of detection. So first one, and actually this one, drift detection mechanisms, was one of the founders, let's say godfather of this mechanism, is the João Gama that I showed his picture. So drift detection method, DDM, was created in 2004, and after that, a lot of scientists up to now, so it passed more than 20 years, continue to publish new papers with the base of DDM model. So EDDM and RDDM, the abbreviations often says early drift detection method and reactive drift detection method, are based on the paper that was published in 2004. There are also other mechanisms, and probably this one, is something that you instantly will think about when you're talking about this topic. Okay, I can create two windows of the data set and compare them. So based on these windows and statistical based mechanisms, we have approaches like ADWIN, adaptive windows, that we will talk a little bit later about this one. And also you can use, for example, Kolmogorov-Smirnov test to compare distributions and find out if your data changed. There are also cases when you need unsupervised and semi-supervised learning mechanisms. This one is specifically good when you have unsupervised data and you try to classify, for example, your customers to different groups. And if you remember, I showed the case where we have as a drift type new class. And unsupervised and semi-supervised methods are specifically good for detecting the new class in your data when you are creating. And for example, if it's something that you offer as a service, you will understand, okay, I have new type of customers that I have to provide new type of product for them. And of course, there are two types of models that are, more popular in also other fields. Ensemble models that just combine different types of algorithms, and also neural networks. You have non-linear environment. Environment, there is no linear relationship between your data or different sources. In these cases, you might use also neural networks. Of course, each of the cases, drift detection mechanism, has some pros and cons, and you have to understand based on your specific data which one is good to use. So sometimes you need to have high accuracy, and computational costs for you have to be low. So in that case, you might go with DDM, or you need higher accuracy, but you don't have any problem with computational costs. In this case, you can use just neural networks for your specific task. So, in this field, when you are working with concept drift and you try to, for example, classify some model or to understand how fine it works, you have to understand which datasets are used in this field to make comparison between the studies that are made. So the benchmark datasets. We're going to speak about these datasets a little bit, and also there is one framework that I will discuss in the end also, more framework, massive online analysis, that allows us to make experiments easier in the field of concept drift. But now let's speak a little bit about the datasets, and actually there are a lot of datasets, but these ones that I presented here are most famous ones. So it's sometimes very hard to find real data to work with. That's why in this field there are a lot of synthetic generated data sets with different options, variations that you can create or generate yourself that will work on specific case of the data, concept drift. So depending on its abrupt, gradual, or other cases, and etc. Or also you can just find some real data sets like card, weather, and also there is some other data sets like airplane, and etc. But these are the main data sets that, okay, if you decide to work with some concept drift detection mechanisms, you will understand that, you can use these data sets as a benchmark to understand how well performs your data compared with the state-of-the-art of the models. So easy to find in the internet, and also you can use just the MOA framework to extract them. Sorry. So when we're making literature review for this specific problem, we find out that there are three main cases that are not very there is no much information about these topics. There are not too many papers published. So first case is when we have unbalanced data set. In this case, concept drift detection problems becomes more difficult to understand in your data. And this is one of the cases that is not very well analyzed. Another problem is that concept-driven detection in textual and image data sets also not very well analyzed now. And one of the interesting things that, to be honest, initially I thought that it's, well, something bizarre, is that concept-driven detection is mainly looked in the classification problems. And there are very few papers related to regression problems. So if you will be interested to make, well, publish a paper and you are interested, okay, where I have to look, these are the main cases that there are a lot of gaps that you can review and understand where you can make, publish a paper. Okay, so now let's speak about the model degradation, and in this case our our discussion will be divided into two main parts. In the first part, we'll discuss some problem with the image classification on a simple data set. And on the second case, we'll just review tabular data that will also make some drift detection. We'll use some drift detection mechanisms to understand how it detects and how it changes. So, before going to image classification problems to discuss it, I just want to bring one real fun example from real case that happened with one of my colleagues. So they were making a model to separate based on image, male from female, and on their trained data it was working completely fine. So accuracy was very high for both classes and there was no problem. But when the data went to production, what happened is that it started surprisingly working very bad on female. So it was having some problems to classify if on the picture on the the person is female or not. So it appeared that their data has some drift. The input data shifted, and what happened that they find out that in their data set, well, they trained the model, all female characters have their eyes closed with their hair. And in production, when they put it, they noticed that new person that arrives, they woman put their hair behind their ears. And in this case, the model thought, okay, if I see ears, then it's man. If I don't see ears, and it's covered with hair, then it's female. So this is type of drift that happened. And you never know what can happen. So in this case, when we're going to discuss, of course, not like a hair, but we're going to generate some different types of drift. And specifically in this case, it will be noise, blur, rotation, and brightness. So we're going to train a normal data set, then add some noise, blur, rotation, and brightness, and to understand how our model continues to work. So in the last few years, there is also very high trend about the explainable AI techniques. And we're going to use also GradCam to understand if the models that we created how they perform with the drift and without drift when we are trying to understand why this or that decision was made. And one of the things that I decided to do is also to understand, can the statistical methods find out where we have drift change in our data set or not. So for this case, we're going to use some simple data set, CFR10, that has 10 classes, and just as a model, ResNet 18 with slightly modified architecture. And also we're going to generate 4 different types of drift. So noise, blur, rotation, and brightness. Generally speaking, our whole workflow will look like this. So we start with just training model on CFR10 dataset, then generate GradCam heat maps, compute baseline matrix on normal dataset, original data, and also on the same trained data, after training the model, we're going to apply drift on the test data, compute matrix on drifted data, and compare this matrix and also compare the GradCam heat maps of our original dataset and drifted dataset. Additionally, in the end, we're just going to make some comparison based on the statistical tests to understand whether we can see some differences. You understand why we need this on the next slide. But in the end, we just will analyze our results to understand how severe the problem may become. So when we're speaking about the GradCams, main goal is to understand why do we classify image to the class 1, 2, and etc. So GradCam heat maps helps us to understand in our decision that we made which parts are the most significant that impacted to our decision, well, to model decision. So let's look into the example and the first row. Just let's forget about the second row now. So we have the trained data heat maps, stacked heat maps, and also we have test data heat maps without drift. We can see visually that, well, they're completely similar, very close to each other, let's say. And now on the 4 next images, what we do, we add some noise, brightness, rotation, and blur to our data to check out how severe our decision, well, GradCam decision making may become worse. So what happened in the case of the noise? Now we see that for the class 8, that initially our data decision boundaries, well, the highlighted areas are these 2 angles, and now only the left top corner was left. In the case of the brightness, well, in this case it left, well, almost the same, but there is also some differences in the center area. In the case of the rotation and the blur, we also have some differences. So, for example, in this case, we see that, well, there is no yellow light here, and in this case, this one becomes more brighter. However, okay, we can say, yeah, GradCam in most of the cases, generally speaking, we'll see that there is some change in our data. That's why the GradCam heatmap changed. But what can happen also, that visually when you are reviewing this, you will see that, for example, in another class, for the human eye, there is almost no difference, and you will say that, okay, in this case, GradCam thinks, even though that we added some drift in our data and model accuracy significantly dropped, in this case, we see that it doesn't see any difference here. So that's one of the problems with the GradCam. So now, besides visually reviewing it, when you're, well, I believe when you are working on some type of research, you have to look into also numerical results. So in this case, when we're adding noise drift, to be honest, I was not working very intensively to have a very high, good performing model. So forgive me for the 73%, but I believe for our just example, it's fine, completely fine when we have 10 balanced classes. So 73%, and these SSIM and IOU might be not so much familiar for you, but the first one is similarity structured index, and second one intersection over union. So what we're comparing here is the GradCam heat maps, the differences between, well, and also the model accuracy when we're adding the noise type of drift. So in this case, we can see that when we're adding noise, gradually, well, not gradually, but rapidly, the values of the accuracy of our model decreases. So it becomes completely useless model. And the problem also, we see that SSIM and IOU, so maybe I should name without the abbreviations in the future, but yeah, also decreases. So initially it was like 98%, 95%, not very low, but after that we see that it significantly drops in the case of the noise. Same happens with the blur, and actually this one initially starts to act severely compared with noise, because we saw that during the noise it was 73% and 72 and etc. But in this case, when we are adding to just blur, it drops, but after some time it becomes more or less constant. So that's with the blur case. About the rotation drift, well, most of the cases when we're creating some models with the image datasets, we usually include rotated data because we say, okay, if I rotate the data, I have new data, new samples, and I can use it for the training. But for the experimentation, for this case, we just decided not to include it, and we see that, okay, even in this case, it might decrease the accuracy of our model. And brightness, actually, this example about the brightness, one of my colleagues from the university in Lisbon had such problem when they were making some model to publish a paper related to some images. They noticed that their data works fine when it's a bright image, and then when the images are taken at night, it has significant problems. So after I also introduced him about this topic, about the concept drift, so what can happen that even the brightness may have significant impact on your data. So for example, you are taking images in normal room with the normal bright, and then you add it or just remove completely light and have very small amount of light in your room, and you are taking pictures and then try to classify them, you may have a problem with the accuracy of your model in this case too. Okay, so that's about the brightness, and in this case, as you can see, the accuracy also significantly drops. Additionally, one of the main goals is to understand, okay, we see it, but visually, as you remember in our heat maps, it's not always that we see some difference. For example, for the class 9, no visual difference at least for me. If you see any difference, please let me know. But okay, can I just take some vectors from the heat maps of the values and compare the distribution of these values? Maybe there is some difference that statistical tests will help me to understand. So that's why I decided to use 4 different tests. First two are Kolmogorov-Smirnov test to compare distributions, and also Anderson-Darling test, and 2 other tests, t-test and Wilcoxon test. And yeah, my main goal was to understand whether we see some difference there or not. So what we are comparing here, we have drift type, noise, class, and the comparison of the 0.1 intensity between the original heat map and with the heat map with the drifted data. So we see that in this case, Kolmogorov-Smirnov, okay, find some differences, and the rest of the models fail. And also for the, however, for the class 9, we see that, okay, visually we don't see any difference. In this case, we see, there is also significant difference, but for other cases, okay, for Anderson-Darling we also have difference, but for the rest of the cases there is no difference. So same is for the rest of the cases, but I don't believe it's necessary to go through all the points. Okay, and what is, well, surprising here, sorry about that, is that initially I thought that, okay, Anderson-Darling probably works fine, but no, it actually also doesn't perform well. So we see that it doesn't see any differences here. Okay, so we see that in this case that they do not see any difference too, but in most of the cases, but the Kolmogorov-Smirnov tests show some hope to find out if there is some difference or not. In other cases, it's a little bit difficult. So now let's look into another example, but in this case not just to show the severity of the problem, but to understand how we can integrate some mechanisms to see if it will help us to improve the model accuracy or not. So that's why we're going to look into some, well, we'll use some tabular data, create classification simple model, compare the the model accuracy without drift detection mechanism, and also we'll use model with drift detection mechanism. And if you remember in the first slides, I mentioned about the algorithm Advin that opens as adaptive window mechanism. So the general idea of this algorithm is creating dynamic windows of your data, and when we are receiving new data point xt, it's added to our window W. Then we're just comparing these differences of average values of different cases of the splits of the windows, and we check if the average difference between of these two windows is higher than provided epsilon value. That is just a threshold for decision making in our case. If there is some drift, if this criteria is met, we say that okay, we detected some change in our data, we drop all data, retrain the model, and create a new window. Otherwise, just our window continues to grow. So, idea is very simple, and in this case, we are going to use this data set. So, this is a very simple example in this case, but in reality, the problems might be more severe. However, I guess to understand the main example, it's easy to review on such type of examples. So, initial our data has a distribution like this, where we see that if attribute 1 and attribute 2 have the value of 4 or less, then our decision boundary, well, changes. So if it's higher, then it's class 0. If it's lower, then it's class 1. After some time, our data becomes like this, that decision boundary becomes 5 for each attribute. And for the third case, it becomes 9 and then decreases and becomes 7. So, yeah, this is the main data. So if we will train a model initially on this data, and after some time our data changes and we receive new observations like this, main part that it will fail, the predictions will be this part. And this one will be fine. So we'll lose some classification accuracy, but after some time, when the new data arrives, it will severely drop, and then, yeah, it will continue dropping because also it changes. So, if we make just some, let's say, some model, tree-based model, decision tree, we can compare the distributions, differences of the confusion matrix in our cases. So in this case, we'll see on the left side with the drift detection, our accuracy is significantly higher, and in this case, we have large volume of observations that were fairly predicted. So the class was predicted not correctly. So what happened if you do not update your model? This is one of the most problems that will occur. So one thing that I want to say before going forward, and I hope to receive this question during the Q&A session, is what if I will integrate just some active learning mechanism in my model, and it will receive all the time new points and will try to learn the data. That's one of the tricky questions that I will mention in the end, but it will not always work as expected. However, there is, well, in this case, as you noticed, there are also some observations that we didn't classify very well, and you will say, okay, but the decision boundary is very easy to find. Why do we have so many misclassified points? So actually the example that I prepared was very easy, without any going deeper to make it perfect. So what we can do to make our models drift detection models to work fine is the following. Let's say to understand if you have drift in your data set, you are tracking model accuracy. Okay, when you detected some drift, you see that, at one point your accuracy dropped, you detected it. You have to have some recovery time to understand, okay, after some time at first, let's say, skipping first 100 observations after detecting drift, you say just some waiting time to have stabilized accuracy of your model, and then use the drift detection mechanism again. Another thing that you can do is use not only one algorithm to detect drift, but use several algorithms and do not rely only on one. Another thing is that you can add early warning mechanisms. So most of the models also have such thing that they not say that, okay, drift is detected, but if they notice some slightly change in your data distribution or in accuracy, they are providing you a warning that say, hey, look into this. Maybe there is something which is changing. So you are looking into that warning and say, okay, this is fine. Maybe there is because of this outlier and everything is fine. There is no drift and etc. So early warning mechanisms can help you to identify the drift faster. And one of the interesting things that I noticed is you have to also monitor the feature importance. So let's say you are making some classification model, again, or just working on a regression problem. For simplicity, let's use logistic regression, or in the case of just regression with the continuous variable, just linear regression model. And you see that feature 1, p-value was very close to 0, and you see that, okay, this is very important feature, I'm keeping this in the model, but after some time when you're receiving new data and you create again new model with that, you see that it become, well, non-significant feature. Okay, what changed? Maybe there is some drift. So feature importance, tracking it is very important to understand, because if this feature was important, maybe it become also, well, probably not important and you have to make some change, or there is some change in your data and that's why it is not important anymore. So what happens when you are speaking about the concept drift? There are several things that pitfalls that a lot of people make and think that, okay, this is drift or not. So there are common mistakes. First one is confusing noise with drift. Having just one point of outlier or 2 points of outliers in your data, it doesn't mean that you have drift. It may happen that, okay, because of some technical problem, you received corrupted data and the values are not correct, but it doesn't mean your data shifted. Your model continues to work perfectly fine on the rest of the data in the future. So noise is not drift. Drift is when your data distribution changes, not just because of one outlier. One of the funniest thing, and to be honest, this happened to me first time when I was working with the concept drift detection, that I integrated mechanism for drift detection, but I forgot to retrain it. So what happens that you think that, okay, if I detect drift, it should retrain automatically, but no, it's completely on your hands. So you have to retrain it after detecting the drift. So you detected it, you are retraining based on some new data that you received. And one of the important things is that only monitoring accuracy, it doesn't mean that in your data there is specifically drift. It's very close to the noise, but yeah, just monitoring accuracy is not enough, because also we saw that virtual drift is the case where our classification model works fine, but in reality the feature distribution changed. So this is type of drift that you will not see with just monitoring the accuracy. Another thing is that you have to understand which type of drift detection mechanism you have to integrate, because if depending on the nature of the data of your problem, you might see that the different approaches will work fine. So choosing the best approach is very important. And also ignoring feature drift. This is similar to this one that I just mentioned, that most of the people concentrates only on the target variable and forgets that input space also can change without affecting the target. Also, you have to use some other mechanisms to review it and understand if the data changes. So for example, just integrating mechanisms and forgetting about it is not enough. So in some cases you have to have also some person that has, for example, information in the field and provide you updates, and you know that, okay, time to change the model. So I already mentioned about the model framework. I provided the link, probably it will be shared with you. And also there are 3 main libraries that if you will be interested in this topic that you can use. First one is the River, Scikit Multiflow, and Foros library. To be honest, all of them, personally, in my opinion, have some problems when you try to integrate in your environment. But yeah, these are the main libraries that you can work with to understand and solve different problems related to the drifts. Okay, so every time when I'm working with some concept drift detection mechanisms and I prepare slides, I always try to finish with this same citation of Heraclitus, that there is nothing permanent except the change. Of course, he was speaking not about the concept drift detection, but about the life. But I believe this one is perfectly fits for drift detection mechanisms too. So our models that we create are not permanent and they are changing. So thank you very much. So now I believe we'll have some Q&A session. And this is the QR of my LinkedIn, so if you have questions in the future, we can connect and I am free to listen to your questions. So,
thank you. Questions?
Okay, so during the presentation, when I was speaking, I said that I hope to receive a question about active learning, why it will not work so good. So let's imagine that this question someone asked. So why it can work fine all the time? Because you see, when you have drift and you are just adding new observations in your training process, it might happen that all the observations that had one class, let's say class 0, in our case, they become in the new data class 1. And now, for the same part of your data distribution, you have points that have both values with the class 1 and class 0. So your model will be confused. Okay, now in this part of the data distribution that I have, should I classify it as 0 or classify as 1? So that's why active learning mechanisms without drift detection will not always work. So if you have some drift, you have to just remove the old data when you detect and use the new part of your data to retrain the model. So yeah, that's because not always active learning mechanisms without drift detection will work. Okay. Yes. Okay, sorry, there is a microphone.
Thank you. My question about, in your experience, like work experience, with which kind of data you work it with, and do we have like differences how to manage like drift detection with variety of kind of data? Like.
Okay, so if I understand the question correctly, so you said that in which field I notice drift and which mechanism will work for the specific cases. So let me go back to one of the slides. Sorry. Okay, so almost there. So, I noticed, well, I worked with the drift in 3 main domains. First one is semiconductor industry. Second one is related to biological data sets, well, medicine mostly. And third one is recommendation systems. But there are also examples from the financial world and etc. So what is the main point? Well, depending even in the field, it doesn't matter. It's semiconductor, biomedical, etc. The most important thing is not to say that in this field works Edwin or in this field DDM, but to understand the nature of your drift type. Because the algorithms that are developed, some of them work better on depending not on the type of field, but on the type of the distribution. So what I want to say is, in this line. So depending if it's sudden drift, incremental drift, gradual recurring drift or gradual drift, depending on the type of drift, one algorithm works better than another one. So for example, if we have some sudden drift, based on my experience, Edwin algorithm that I described works better. But if we have, for example, gradual incremental drift, that changes are happening gradually. In this case, you might use reactive drift detection methods that have very small delay on finding out the drift, and in this case, okay, they will work fine. But if you are using, for example, some model that works fine in the incremental case, and you know that from the nature of your data that sudden drift is something that may happen, with the incremental drift detection mechanism, minor change will be detected as a drift in case if you think that you will have sudden type of drift. So there is minor change, it was detected as a drift, but actually it was some just noise at that moment, and it was not drift. So it's not about the field, but about the nature of the drift type that you have to understand which one is better for you. So yeah. Thank you too. Yep. Mana.
So you said that you worked in biological field, and my question is like, how did you understand which version of this you need to use to detect the drift? Because biological field is so confusing. Like there are so many health issues that can happen, you know.
Yeah, actually, my case was related not to tabular data sets, but was related to images. It was related to images, and initial data that we were receiving, that we were analyzing, I noticed that visually, after some time, the new data that we arrived, the source was different, and we saw that there is some differences in our data visually. So actually, initial part that how we noticed that was this, but then we decided, okay, in this case, if we have some type of drift, then we have to have some also mechanism to read. So actually, it was very easy to notice, but I understand your question. It's very important, and yeah, for the specific biomedical case, it's very difficult for me to say which one is best. In the case of images, it was easier for that case. Okay. Yeah.
Also, what kind of drifts do you notice in LLMs, bigger LLMs like nowadays?
What can happen?
Like, for example, I think that most drifts are coming from when you're giving the prompts and it's using the same prompt for feeding itself, and it's getting a drift after that because the data itself is changing. Like, because of the prompts feeding, like LLMs usually like thinking part of it is like getting the prompt back to it to understand the topic better. So it's giving the prompt itself back. So what kind of drift is it? Is it like incremental drift, more like, or?
That's a very good question. Thank you. So I believe in this case it will be incremental because let's generalize your question. For example, I was thinking about the LLMs, how this may happen, and one of the examples is that, for example, you create new model only using British English, and then you are giving to users in the United States, and they're starting to use US English. So if, we know that there are some differences, not so much, so big, but for example, in case of the Armenian, from different regions, the accents or the dialects might be so significant, different, that sometimes even we don't understand each other. So drift may happen when you train on some type of data that, well, in this case, just language, okay? And the users use the same language but with other dialect. So, and model will probably see some words that it doesn't know, and maybe there will be some problems to understand the main concept of the question that you asked. So, but in the case of the prompts, I believe, well, to come back to your main question, I believe it will be the incremental type of drift. But what was I thinking that in example that I provided is more like to close to sudden drift, because you train on one dialect and then it's completely another, and sometimes even we don't understand that, yeah, we are providing it's sudden, but your case that you provided is, I believe, also incremental. Okay, I believe so. So, yeah.
There are no any other questions. That's it. Thank you.